I'll begin with a word of prayer. Dearly Father, we thank you for this day. Again, I thank you for this class and these students, and just ask you to bless our work today, Lord. In your name I pray, Jesus. Amen. So one of you guys asked me to visualize the limit that we calculated last class, and this is it. I said there's pictures in the notes. That's true, but here's that website I posted for you guys. And so what you're looking at, first of all, this is the graph of z equals to 2x squared y divided by x to the fourth plus y squared. And what I've pictured here is a couple of different parabolic paths. So like up there, the blue curve is what happens when you get x equals to t, y equals to t squared, and then plug those into the function, right? So it limits to like 1 as t goes to 0 for that path. This one, the red one, is x equals to t, y equals to minus t squared, and then plug those into the function, right? That path limit, it's down here. It actually limits to minus 1. I think if I can, or maybe, wait a minute, I may have the wrong. Oh, that's the green one. Yes, thank you. Yeah, thank you. The green one goes to minus 1. You can kind of see it if you get. Like I said, these kind of visualizations are of limited utility. It's kind of a pain to actually see things, but if you can use your imagination a bit, there's the green like that as it goes through like where the origin is, it hits minus 1. So we have two different parabolic paths, one which goes to 1, one goes minus 1. Since the two path limits don't agree, the limit doesn't exist, right? Now, on the flip side, I also have plotted here, if you can use your imagination, let me get off the parabolic paths. I'll uncheck those. All right. There's also that red path there. That actually is the trace along a line approaching the origin for this graph. So like, if we follow a line, it ends up going right through the origin. You can't see it entirely here unless I think if I hit this button, there's kind of a wireframe of the path, and you can see how that goes through the origin. And it turns out, for this particular example, if you take any line that goes through the origin, any line that goes through the origin in the domain, and you look at like the resulting path along the graph of the function two variables, all of those paths end up just going through the origin, so the limit's 0. That calculation is shown in the notes in that I plug in a line of arbitrary slope m, and they all limit to 0 for this example. And yet, if you plug in a parabolic path, you get different values. So, like, that's a picture for it. If you don't like this one, you could also play around with, there's this GeoGebra 3D grapher, which is also good. So here is the same function, and what you're looking at in the black is currently a plot of this curve, which is t, mt, and then I plugged in x equals to t and y equals to mt into the formula we're looking at. All right, so this black is this is the trace. This is actually the points on the graph which are obtained from plugging in a line of slope m going through the origin. And the cool thing about GeoGebra, of course, is you can play with this slider here, which is super nice. And if you look at different m's, if you look at that black curve, they're all doing what? They're all going through the origin, which is kind of cool, right? And then, if on the other hand, instead of looking at lines through the origin, we look at, let's say, parabolas through the origin. I'll turn off the lines here, if I can. So here's parabolas through the origin. I've got a parabola like of the form y equals kx squared, and this right here, so if I change that, you can see that the path does not go through the origin, right? In fact, if you go through different k, you approach different values, right? And so this illustrates the fact that the path limit is going to be negative down here. It's going to be 0 right there, and then it's going to be positive up here, right? So depending on which parabola we approach the origin, we get different values for the path limit, and therefore the limit doesn't exist. All right? So when you asked me how would you visualize it, you could do this, but it took me 40 minutes to set up, and I don't think it's really worth it. That's why I don't do this. All right? So I think algebra is a better, a better way. But we should keep this in mind if we're ever like in the dark about how to visualize something. It's something we can always, get out and look at. So. Yes, sir. I'm sorry, what?
Would there be like a test where we'll have to like draw this out on like...
Will you actually have to draw things by hand on a test?
like the giant like 3D curve in reality.
Well, I do. It does become important that you're able to visualize 3D things by hand. That's true. Like that's why we've gone over the different. This is a paraboloid. This is an ellipsoid. This is a hyperboloid. All those things. This is a plane. So I can't say like universally no, but like would I expect to be able to graph that by hand? No, I can't. Like I can't. These things that have tears, like basically this has a tear at the origin. There's some kind of like, if you were to try to like, take a sheet of paper and like bend it to make the graph of that thing, you've got this like tear at the origin. It's hard to visualize. Anyway, so another example here. What if I have the limit of x, y, z goes to the origin, goes to 0 of, I don't know, how about goodness gracious, I'm trying to think of a good one here. Secant of the square root of x squared plus y squared plus z squared times the tangent of the square root of x squared plus y squared plus z squared. I just made this up, so it may blow up in my face. I haven't taught Calc 1 lately, so I don't know. This could be interesting or not interesting. I don't know. We'll see. What would you... So here, like, this is pretty much tailor-made for doing what? Yeah, we should use a spherical change of coordinates, right? So if you think about this, we can replace this with a limit as rho goes to 0 of, well, the secant of rho times the tangent of rho. Right? Now here, remember rho is the square root of x squared plus y squared plus z squared. It's a spherical radius, yeah? And sorry that test 1 didn't test much on that. I did have a question that was more about that, and I kind of scrapped it because I thought there was enough there already. But we will get back to this. It's totally unavoidable, like in test 3. Test 3 necessarily involves the spherical and cylindrical coordinates and such. Test 2, still a little bit, but not as much. But anyway, now what? Well, tangent of 0 is 0, right? Secant of 0 is 1. Oh, I'm an idiot. We didn't even need to do this, right? This is dumb. I'm sorry, this is dumb. We didn't need... I'm a dummy. We could have just done this from the start, right? The answer is 0, right? There's no... This is not even... This is not an indeterminate limit. Remember my first rule for calculating limits? If you can plug the limit point in, just do so. That applies here because secant of 0 is 1. Tangent of 0 is 0, so 1 times 0, 0, right? We didn't need this sophistication here. My apologies. Let me try to come up with one which is a little bit more exciting. How about cosine of x squared plus y squared plus z squared minus 1 divided by x squared plus y squared plus z squared. All right, there we go. This has the badness, right? This is a baddie. Cosine of 0 is 1. 1 minus 1 is 0. And this is type 0 over 0, right? This is a genuinely indeterminate limit. We can't just plug in the limit point here. What do we do? So, again, this is tailor-made for like a spherical substitution. So I make, this is the limit as rho goes to 0 of cosine of rho squared minus 1 divided by rho squared, right? Now, I think what I would do at this point, I say it's type 0 over 0, right? So we can use L'Hopital's rule. Here's my notation for that. This is type 0 over 0. And L'Hopital's rule says what? Take the derivative of the top and the bottom, right? Exactly. So we got what? We got minus 2 rho sine of rho squared divided by 2 rho. And so the rho cancels, right? And we're just left with a limit as rho goes to 0 of minus, the 2's cancel too, right? So just minus sine of rho squared, right? At this point, we have a continuous function. Like sine is continuous at 0, we can just evaluate at the limit point. The answer is like minus sine of 0, which is also known as 0, right? Do I have everybody's bonus question? Because it's, make sure you turn it in. I'll get them. Thank you. I thought I should check it, make sure I got them all. You got to catch them all, That's what they say. Any questions about this? Yeah.
Just if we get 0, don't we do it again?
But sine of 0 is just 0. Here we don't. This is type 0 over 0. That's true. And you could apply L'Hopital's rule again, if you wanted to, I suppose. But the thing is, I have a 2 rho here and there. So they just cancel. I'm just left with sine. Yeah? Yeah. Now, if we did what you're saying, we'd get the same answer. Check it out. L'Hopital 0 over 0. That gives me, I may regret this. So the product rule gives me minus 2 sine of rho squared plus 2 rho times 2 rho cosine of rho squared divided by 2. But again, this whole thing is going to 0. So you get 0 over 2, which is still 0. But I think in this case, algebra is easier than L'Hopital's rule, right? Agree? Yeah. Can I come up with a more difficult example for this? What do you guys think? How about this? What if we're up against, like, the limit as xy goes to 1, 2 of, I don't know, the hyperbolic sine of the square root of 1 minus x minus 1 squared plus y minus 2 squared divided by the square root of x minus 1 squared plus y minus 2 squared. What would we do with this thing? Thank you. Did I ever resize the... I can't remember if I had it zoomed out for the... Yeah, we're good. Cool. So I can't just use... So something like this requires a little bit more creativity, right? So one of the things we haven't done yet much, maybe at all, is suggest that we could define kind of polar-like coordinates at other points, right? Like I could essentially think of introducing, say, I could do something like x minus 1 is equal to s times the cosine of beta, and y minus 2 is s times the sine of beta. So basically I'm saying x is equal to 1 plus s cos beta, and y is equal to 2 plus s sine beta. So the idea here is something like at the point 1, 2, right, you can go to a point out here, right? And you'll have distance s from that point, and you're sweeping out beta relative to that. So this is modified polar coordinates is the idea, all right? You could look at modified polar coordinates, and in these modified polar coordinates, it should be fairly evident that this is actually the limit of what? This is the limit as what? What goes to 0 at 1, 2? Yeah, s goes to 0. So we should do the limit as s goes to 0 of the hyperbolic sine of s divided by, well, s. Now, hyperbolic sine of 0 is 0, right? So this is, yeah?
Why isn't it the square root of s? Oh, never mind, because that is the hypotenuse, never mind.
Yeah. I mean, these are basically constructed so that x minus 1 squared plus y minus 2 squared is s squared cos squared beta plus s squared sine squared beta. That's a good question, which is just s squared. So yeah, s is for us the square root of x minus 1 squared plus y minus 2 squared, right? Okay, but this is a limit type 0 over 0, right? Yeah, so we could use L'Hopital's. Assuming we know how to differentiate sinh, right? Do we? If you don't know what sinh is, you need to review that. That is part of this course. So the derivative of sinh is cosh. And the derivative of s is, well, 1. And so this is just cosh of 0, which, by the way, is 1. So the answer to this is 1. All right. One final example for multivariate limits, and then we'll stop with this. What if I was up against something like the limit as xy goes to, let's say, absolute value of x plus the absolute value of y divided by x plus y. Yeah, I need to, goes to what? Yeah, thank you. Oops. 0, 0. Yeah.
Would you have to take the negative of both, take the limit as it goes from the left and then the limit goes from the right?
Well, what does left and right mean?
Like, never mind.
I mean, no, seriously, like
As in on the graph, because it's the absolute value, so would you have to take the negative side and then the positive side? So like the limit from the negative x.
let's try to graph this for a second. I like what you're saying. Graphing it's kind of hard, but if this is x, let's see what we're up against. I mean, you're asking you're asking good questions.
Why is this 3D?
Because we're looking at, why is it 3D? Because we're thinking about z equals to f of xy in order to understand this limit graphically. And so in order to understand this limit, we have to, okay, so like, we think of xy, the xy plane, as a place for the domain of a function of two variables. This is a slight abuse, right? I mean, technically the graph, the domain of a function of two variables is a subset of R2, right? But we can identify R2 with the xy plane. And so, all right, so if we think about, quadrant 1 for x and y, if x and y are both positive, then the absolute value of x is equal to x, and the absolute value of y is equal to y, right? And f of xy in this context is, well, x plus y over x plus y, right? Which is just 1. So this is a kind of boring function in some sense. Its graph is just up here at 1, right? this is z equals to 1. It's not a plane, though. It's a quarter plane. And in fact, same story. I can't graph the full. That's all I can do. Because the graph gets messy past this. See, how about y and x and y both less than 0?
It would be negative.
Yeah. What'd you say? It would be what?
Negative.
-1, right? Because it's minus 2 over 2. Well, anyway, that cancels to -1. So back here, right? I can't grab it. I can't do it. Actually, maybe it's helpful to just look at this sort of like a top-down picture. So here's my y, here's my x, right? And what I'm saying is it's pretty clear that we've got z equals to 1 here, and down here we've got what? Z equals to -1 for the graph. But what about the other ones? Maybe it's also clear. If we have x is positive and y is negative, then f of xy is what? We have absolute value of x is x, but absolute value of y is -y, you see. And that's not 1 or -1. That's complicated. Right? It's complicated. 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 Because like this, so where is this? X greater than 0, y less than 0? This story happens here, right? And over here you'd have what? You'd have like y minus x over x plus y over there. So what do you guys think about this limit? With this, we've thought about the graph a little bit, right? What do you think about the limit? Yeah. I don't think it exists, right? How do we prove it doesn't exist? I mean, you could say, well, the graph is complicated. That's not really going to work for us in here. We just need to find two path limits which don't agree. That's all. So I suggest it's fairly evident that if we look at I think if we look at this one, we're probably going to get into trouble, right? So if we look at the limit, let's see how that works out, of x comma x goes to 0. So this is a slick notation for path limit that you guys can also use if you want. If you notice in my notes, I usually use like r of t and write out the parameterization of the path. But if you want to use x as a parameter, we can do this, right? Like this, what this means is I'm putting y equals to x in the limit, all right? And so this is a slick notation for the path limit. We've got the limit. What this means then is the limit as x goes to 0 of what? Well, absolute value of x plus the absolute value of x divided by x plus x, which is what? Limit as x goes to 0 of absolute value of x over x, right? Because we can cancel the 2. But remember the deal. The limit as x goes to 0 from the right of absolute value of x over x is what?
1.
It's 1, right? Because that's x over x, which is 1. Versus the left limit, we have absolute value of x over x is equal to limit as x goes to 0 from the left of minus x over x, which is also known as the limit as x goes to 0 from the left of minus 1, which is equal to minus 1. So therefore, this limit does not exist. Because the x goes to 0 plus or minus limits differ. That's calculus 1. In calculus 1, we have this theorem that if the left and the right limits of a given single variate limit don't agree, then the limit doesn't exist. And then, logically, therefore I've shown that this path, the limit along this path to the origin, gives a non-existent limit. And that's enough. If one path has a non-existent limit, the multivariate limit fails. Because the theorem is that if the multivariate limit exists, then all possible path limits must exist. If even one of them fails to exist, game over, we're done. All right? So. Okay, so I'm going to move on then because, I don't want to give this topic more airtime than it deserves. It is a relatively small part of what we're doing going forward. Really, what I'm about to introduce is far more important. And so what we're about to get into is the topic of partial differentiation. But in order to understand partial differentiation, we must first understand what is the directional derivative. And before we understand what the directional derivative is, we need to understand the question that it's trying to answer. The question is this. And by the way, so here's the deal. We're going to be we're working with functions of two variables for the most part in here. And so this is how I have the notes structured. I study partial differentiation of functions of two variables in some depth. And after that's all settled, then we'll circle back and look at functions of three variables or more. All right. So our context is we're given a function with two variables, and we're trying to understand its change. So let me write that out. So here's the question. Given a function of two variables and a point, let's say, let me try to use my notation, x naught, y naught, which we'll also call p naught, all right, in the domain. How does, f of xy change at this point? Right? So think about that question for a second. We just had this conversation, left versus right. Right? Does this question even make sense without further stipulation? We need to add something, don't we? In order to understand the change of a function of two variables at a point. Because we can't just study the change as we go across the graph. Y equals f of x, right? Yes, the change at a given x value. That makes sense because there's only one thing to do. Read the graph, left to right, right? So you can ask what's the change in a function of one variable without further at a point. That's enough because there's just left and right. But here, we need to also supply a direction in order for the question to be meaningful. So in the direction, let's say u hat. All right. And my typical notation for this is AB. All right? So how are we going to calculate the change in the function of two variables at a given point in the direction, like the AB direction? Let me hazard a picture of what we're trying to do. So we've got some kind of graph, all right? all my graphs kind of look the same when they're about this kind of thing. So here we're looking at z equals to f of x comma y, right? We've got some point in the domain which we could kind of visualize as down here, right? P naught. And I mean, technically this is P naught comma 0 in the x, y, z system. But I'm just saying visualize the point in the domain according to this point in the xy plane. All right? Now above that, right here, let's say, is the point in the graph. Right? That is, this point up here is x naught, comma y naught, comma f of x naught, y naught. That's the point on the graph. If you want me to, we could visualize the AB vector down here as well, in a horizontal sense, right? So maybe it's like this. So if I think of it I can think of it this way, but of course I'm identifying that two-dimensional vector with the three-dimensional vector AB what? AB 0, right? But I'm just, so down there, right? And if we continue this picture here like that, and if you think about how that intersects up here, right? There's going to be some kind of, place where that intersects like that, yeah? But there's a vertical plane like this, yeah? And so essentially, if I was to, draw that vertical plane over here, right? The curve of intersection of the plane, right, would look something like this. The point P naught we can visualize down here, right? And if you like, we can go like this and go like that. And this would be, I could think of this as like the t-axis, for example. And it's a little bit of an abuse, but I can think of this as the z direction. Of course, that's not the z-axis, technically speaking, because the z-axis is over here, right? But if you move the z-axis over here just for the sake of, whatever. So let me put some quotes on this, because it's not technically the z-axis, but, right? Then the change in the function at this point in the AB direction should simply be the slope of that line. As we look at, slope of this curve rather, in this slice of the graph. And that means we can use calculus 1 to find the slope, because it's just the calculus 1 problem all over again, right? So, what is the blue curve here? If I take this particular point, what we're looking at then is, here we have x naught plus at, y naught plus bt, right? So what I'm suggesting is that down here you could parameterize r of t as p naught plus t times the u hat vector, all right? And then if we look at f of that r of t, we're looking at f of p naught plus t times u hat, which is explicitly f of x naught plus at, comma y naught plus bt. Those are the values of the function I'm interested in to understand how the function's changing at the point x naught, y naught. So the next thing here is f of these two. All right? And so for this reason, we make the following definition. The directional derivative of f of xy at x naught, y naught in the direction of a unit vector u hat equal to a comma b is defined by, well, first of all, this is the notation for it. Big D of sub u hat f of p naught. And that is the limit. Actually, let me see. I'm sorry. I keep forgetting what my definition was. Oh, yeah, I did take the limit. Limit as t goes to 0 of f of x naught plus at comma y naught plus bt minus f of x naught y naught, all divided by t. Yeah.
So is our u hat, is its direction just an arbitrary direction that we picked?
Yep, that's right, because we want to understand the change in an arbitrary direction.
Okay.
I will soon work out one with the specific numbers in it. All right. But can you guys tell me what is that actually, that limit I just wrote? There's another way to look at it, because that's a derivative of something, isn't it? This is actually, if you think about it, the derivative with respect to t of f of x naught plus at y naught plus bt, all right, with t equals to 0 after we differentiate. In other words, if you were to like let g of t equals to f of x naught plus at y naught plus tb, all right, then this is straight up the limit as t goes to 0 of g of t minus g of 0 divided by t, which of course is otherwise known as g prime of 0. So we differentiate g, quote unquote, and we put t equal to 0. That's the directional derivative. And again, that makes sense because of this picture over here. We're studying the change in the function relative to that vertical slice. Now, of course, the directional derivative does not have to exist, right? It would not exist for that last example we were calculating the limits of, right? That function not even continuous at the origin, much less having directional derivatives existing. Well, maybe some of the directional derivatives could have existed. I don't know, but all right. So let's actually work out an example. Well, I guess before I get to my example, by the way, this is my sole, n-dimensional comment here. But if we had f, which was a mapping from Rn to R, then the directional derivative in the u hat direction of f at a point p naught, we can also define by the limit as t goes to 0 of f of p naught plus t times u hat minus f of p naught divided by t, which, by the way, would also be the time derivative of f fed the path which has base point p naught in the direction of u hat. And we just take that derivative and plug t equals to 0. This defines the directional derivative of a function of 3 or 4 or 20 variables. It doesn't matter. All right, so we can define directional derivatives for functions of more than 2 variables. That is my sole comment about more than 2 variables for a while. All right. Just pointing out, this is not just a 2-variable thing. Don't ask me to draw the picture for that one. All right, like I can't draw these pictures that we're drawing for more. More variables. All right, so example, I guess this is 5. Suppose we have f of xy equal to 25 xy. And let's calculate change in f at 1, 2 in the direction of the 3, 4 vector. All right. All right, so work it out. Let's work it out. So we need to figure out here. Okay, so evidently we have my point P naught is 1, 2, right? And how about my unit vector? Now be careful, there's a trap here, right? Is 3, 4 a unit vector? It is not. How can we make it a unit vector? Divide by 5, right? So you guys got me to write 5 there. Good job. I'm easily manipulated this year. So yeah, that's 3/5, 4/5. So there's your unit vector. So we have A equals to 3/5 and B equals to 4/5 in my current lexicon. All right, so in order to calculate the directional derivative, we need to do what? We need to actually calculate f of, let's work it out here, f of x naught plus at comma y naught of bt. In this context, that's f of, what was it, 1 plus 3/5 t comma 2 plus 4/5 t, right? Now the formula for f is given right above. It's 25 x times y. Yeah? Right here. So we'll use that formula. Let's do it. 25, 1 plus 3/5 t times 2 plus 4/5 t. Whenever we can devote fractions to destruction, we do so. So 25 is 5 times 5. So if I absorb a 5 into each of these factors, I get, 5 plus 3t, and I get a 10 plus 4t. And why stop there? Let's simplify the formula. What's the formula here? We got 50 plus 20t plus 30t plus 12t squared. So I believe we're looking at a 12t squared plus 50t plus 50. There you go. That is actually the values that this function takes close to this point in that direction if we use t basically as the coordinate in the AB direction based at 1, 2. That's what this means. So what's the directional derivative? Well, we can calculate now, yeah? So the directional derivative in the u-hat direction of f at the point that we're given. So to be specific, this is the directional derivative in the 3/5, 4/5 direction of f at the point 1, 2. Hey, take that back. ddt of 12t squared, I heard that. 12t squared plus 50t plus 50. And then we put t equals to 0 at the end of that. Unless you guys would rather do limits. You want limits? We could do limits. Derivative good? Derivative good, right? Okay, good. Just checking. So this is, what do we got? 24t plus 50. You got to take that thing and evaluate it t equals to 0. We get 50. So the infinitesimal rate of change of this function of two variables at that point in that direction is 50. All right. Now, the interesting thing is that there's a way to understand this rate of change in terms of how the function changes in the directions of x hat and y hat. So let's calculate for that same function at that same point. I want to calculate the rate of change of the function in the x hat direction and then in the y hat direction and see how that goes. All right, you guys with me? So example 5 continued. So I want to calculate dx hat of f at 1, 2, and I want to calculate dy hat of f at 1, 2. All right. For f of xy still equal to 25xy. All right. So dx hat of f at 1, 2 should be equal to the time derivative of f of 1 plus tx hat, comma 2, evaluated at t equals to 0. dy hat of f at the point 1, 2 is the time derivative of f at 1, comma 2 plus ty hat, evaluated at t equals to 0. So just to be clear, I'm choosing my u hat, my unit vector, for the directional derivative. U hat equals to x hat, which is 1, 0, right? That gives me a equals to 1, b equals to 0, right? On the other hand, u hat equals to y hat is 0, 1. That puts a equals to 0, and my b is equal to 1. And that's why I have 1 plus tx. I mean, that's what this... Oh, man! Oh, no! Ooh! I would totally take off 80% of the credit on your problem if you wrote these things. Man, this is bad. This is very bad. This is so bad. This thing I wrote on the board is so hideous. I'm going to have to add a point to everyone's test. So test 1 plus 1 point to everyone's test. This error is that bad. This is just that bad. Plus 1 point to everyone's test. No. And no. Before I erased those, that was a vector of vectors. This is very, very wrong for this class. Very wrong. If you ever find yourself writing vector of vectors, remember this time. I know 1 point's not a lot, but it's maybe enough for you to remember not to do this. Okay, so intentional errors aside, point being made. This is, we have to take the derivative of 25 times 1 plus t times 2. Plug in t equals to 0. And this guy, the derivative of 25, 1 times 2 plus t. Take the derivative and then put t equals 0. So you guys work this out for me. What do we got? I mean, this is the x, right? And this is the y. So I do 25xy. And this is x, this is y, 25xy. So this is, I mean, this is 50. If you want, I mean, it's that is literally just 50. And this is just 25. The evaluation, just take the derivative, you get 25 and you get 50 here. Evaluation at t is kind of a non-event. Okay, great. How is this 50 and 25 related to the earlier part of this example? I mean, we got a 50 there. So let's see here. The directional derivative in the 3/5, 4/5 direction of f at the point p naught, right? Let me point out that we could rewrite this actually as 3/5 times the directional derivative in the x hat direction of f at p naught plus 4/5 the directional derivative in the y hat direction of f at p naught. If I'm assuming if the directional derivative has this like this property, does it? So we got what, 3/5? Am I right about this claim? I mean, this is a wild conjecture. Okay, it's not too wild. I've done this class before, but conjecture, that's what happened. Is that what happened? X, that's 50. That's 25. What do we got here? 30 plus 20. That's 50. Woohoo! Yes. This is actually not an accident. It's always possible, actually, to calculate the directional derivative if it exists. We can calculate the directional derivative in an arbitrary direction. If we know the directional derivatives in the x hat and y hat direction, we can use those to build the other directional derivatives. So these directional derivatives in the x hat and the y hat direction, they're so important that they have a special name. These are called the partial derivatives. So this is straight up, I'll make the definition more formal in a second here, but this is partial f, partial x in the 1, 2, at the point 1, 2. And this guy here is partial f, partial y at the point 1, 2. Yes, sir?
It uses the same symbol as boundary?
Yep, it does. We won't use boundary that much, though. So usually in this course, at some point much later, you go, we use the same symbol for boundaries we do for partial differentiation, but you know, I messed it up. I used the boundary first. So I should have just not said anything about boundary till later, so you'd have the opposite comment. But yeah, we do. All right, so let me get to it here. Because my larger point to you is that I wanted to calculate the directional derivative like we did today so that you appreciate the geometric origin of the construction. However, as a calculational technique, the way we did example 5 to start with, I said example 1, but that's wrong. The way we do example 5 to start with is not the way. This is not a wise way to do that calculation. There's a better way. And I'll show that to you in just a second here. But here's the definition. Partial f, partial x, at the point x naught, y naught, is by definition the directional derivative in the x hat direction of f at the point x naught, y naught. And partial f, partial y, at the point x naught, y naught, is equal to the directional derivative in the y hat direction of f at the point x naught, y naught. Now explicitly, let's write those in terms of derivatives. What is this? This is d dt of what? Of f of what? And this is d dt of f of what? How do we... So like I just did in the previous example, if we're calculating the directional derivative in the x hat direction, we just add a t to the x component. So like x naught plus t, comma y naught. And then of course we put t equals to 0 at the end of this. Or fix x naught, let y naught vary, let y vary, y naught plus t. Again, put t equals to 0. Suppose you don't want to use t. I mean, well, maybe not say that. I'm not sure I should say that yet. All right, I think that's, yeah, let me, I'll just, Yeah, that's fine.
Wait, so what's before the f what's the symbol?
This?
Partial.
Partial.
Does that
What's that? What does that mean? It means this. That's what it
No,
means.
I mean,
What is?
so like this, so like, yeah, what is, what's it called?
Partial.
It's called partial.
Yeah, it's neither a 2 nor a d. It is, I like verbalize this partial f, partial x.
So it's not even Greek or anything, it's just.
It may be Greek or Latin, I have no idea, but yeah. You probably should ask somebody over there in that tower. They know these things, right? I barely know the difference between etymology and entomology. Sometimes I know that, don't know that. Let's put this into words. So here, this is what this says. This says you differentiate with respect. You differentiate with respect to x while holding y fixed. Right? And this one, you're differentiating with respect to y while holding x fixed. In other words, the partial derivatives are done such that we treat the variable we're not partial differentiating as a constant. Okay? So like, example 6, I suppose. Let's let f of x comma y just equal to y. All right? And I want to calculate partial x, partial, my bad, partial y, partial x. So I got to take d dt of what? Oh, I guess to be clear, I have to put a point in, right? So I'll put the point like I've been doing x naught, y naught, all right? So I'm supposed to say d dt of y naught. Evaluate t equal to 0. Zero. On the other hand, partial y at the point x naught, y naught, d dt. So here, for this one, I'm thinking f of x comma y equals to y to do this, to understand this calculation, okay? So my f, I'll write it out this time, f of x naught comma y naught plus t is actually what? What's this function? This function here does what? It does, I mean, my bad, this is both of them, right? I already wrote it up here. What am I doing? Sorry, guys. If I could remember what I did 3 seconds later, it'd be awesome. So this, by definition, is just y naught plus t. Evaluate at t equals to 0. What do we get?
1.
We get 1. Right. Okay. But these hold for all points. Therefore, we simply write partial y, partial x is equal to 0, and partial y is equal to 1.